Hi, my name is Junio and I'm presenting Mapping Computations in Heterogeneous Multicore Systems with Statistical Regressions on Inputs. This is a joint work from the Universidade Federal de Minas Gerais, University of Pittsburgh, and University of Montpellier. So let's start this presentation explaining what is our goal. So to put it simple, we want to make applications running on heterogeneous multicore systems more efficient. And when I say here more efficient, that could be either execution time, we want to make applications faster, or that could be related to energy consumption as well. So what are these heterogeneous multicore systems? So basically they are the combination of different processing units within a single system. That could be the combination of CPUs and GPUs, CPUs and FPGAs, or even the combination of CPUs and CPUs. And on this last case, that could be the combination of CPUs using different instruction set or the same instruction set. In this case, we're actually being more precise, we're using the ARM big little architecture, and here a common design for this kind of architecture is to have different clusters. These clusters, they have different compromise of energy consumption and computation throughput. In blue, for example, we have these clusters that usually known as little cores. They have a design to be more energy efficient, and in red have the big cores. They have the design to deliver a higher computation throughput, however they are more power hungry. And the interesting thing here is that they share the same instruction set, meaning if you have an application and you generate a binary for that application, that same binary can be executed in both clusters without any change. So what is the challenge associated to this behavior? So to motivate the challenge, actually we are going to show an empirical observation. So here we have a function task which has two formal parameters, s and key size, and basically what this function does is to insert into a global map all the values starting in s. The values, they are associated with a key, which the size varies according to the parameter key size, and this function has a synchronized block, so it can be safely executed by multiple threads. Now remember that we are executing this function on an ARM big little architecture, and we can execute this function on different clusters or even on different processing units for different clusters. So for example, we could use one core from the big cluster and two cores from the little cluster. So for this example function, we observe that when we vary the inputs, the behavior in terms of both execution time and energy consumption, it changes. So here we have this example, we have this chart on the left showing the energy in joules and times in seconds. And one entry here, for example, this one 1B, 1L, it means that we use one big core and one little core to execute the code. And what you can see here for that specific input, that the configuration, the combination of CPUs leading to the faster execution time was for B for L, meaning that we just allow the application to use all the CPUs in both clusters, and that led to the faster execution time. And on the right, we have a different chart for different input, showing that for the same combination of CPUs, that was not the best one in terms of execution time, and actually it was one of the worst one in terms of energy consumption. So basically what these two charts show us is that the behavior of a single function, it can change according to the inputs that we use to execute that function. So this is basically the problem that we have here. So the performance of a single application running with different inputs, it varies according to the combination of CPUs used to execute that code. So this brings the problem here. How can we schedule computations in these single instruction set architectures, heterogeneous systems, take into account the program's input? So let's actually first introduce the related work that tries to handle this kind of behavior, to later introduce our solution. So the first one that I have here is the global task scheduling, a technique that was introduced by ARM back in 2013. The scheduler here, it's aware of the difference between the big and the little cores, and takes into account the dynamic state of the thread when migrating the code. So basically, it observes the load on the thread to define where the computation should be performed. So as it happens at runtime, it doesn't consider anymore the third information about the application, such as the actual program inputs that we use to fed to it. Another solution that we have in the literature is the chomp technique that was introduced back in 2018. Contrary to the previous one, this is a stack technique, so basically it happens at compilation time, and it uses code features for defining where the computation should be performed. The advantage of being a static technique is that it has little to no runtime overhead, as all these definitions on where the computation should be performed. It happens at compilation time, but the drawback here is that we have a single combination of CPUs for that code. So that combination will be the same one for different inputs. So these are basically the main two solutions for this kind of scheduling problem here. And now I introduce the technique that we're developing, that's the GCC Compiler. That's basically the key aspect of our solution, that it explicitly takes the inputs into consideration when defining where the computation should be performed. We have interventions happening at the compilation time plus some feedback that we take from actual runs from the programs. It is adjustable for multiple target functions here that could be either execution time or energy consumption. And this is the general pipeline for our technique. So first the user annotates the code indicating which functions need to be specialized. So in this stage, the users, they can specify which parameters should be taken into account by a compiler. These parameters could be of three types. That could be the formal parameters that we have for the function, that could be also global variables, or it could be expressions that will be calculated dynamically at execution time. In this case, we are collecting the number of threads the application is using. So once this code is annotated, we go to the second stage in which the code is compiled to the bytecodes, and these bytecodes are fed to our compiler. So here basically what we do is take that annotated code and we instrument the application here, adding profile information that allow us to collect the actual values for those parameters at execution time. And we also collect the measurements for our target function. So in this case, it's the execution time. So once we have added this profiling information through instrumentation, we go to the next stage on which basically we execute this code in a training stage. So here we execute the instrumented application with a set of training inputs, and we also use different combination of CPUs to execute that code. So what we have in the end is something similar to this picture. So here we have that for each input, we have the combination of CPUs that led to the faster execution time. So for example, for this first input that we have here, we see that the best configuration leading to the faster execution time was basically executing that code with a single big core. And then we take this training output, that's basically this mapping of inputs to the best combination of CPUs, and we use that to construct our predictor model that's based on a statistical regression. So here basically we have this matrix A that shows the same training inputs that we had before. We have this matrix C here, that's the matrix of target best configuration. So it's something that we observe, something that we collect at the training time. And here on the right side, we have this matrix theta. Then when we are building our predictor, our goal is to find the matrix theta that maximizes the quality of the correct predictions that we can do on the training set. And at last, we have here our matrix of predicted probabilities, which basically obtained by the multiplication of matrix theta by our training matrix here. We also apply an activation function on the results. So basically here on the predicted probabilities, we have probability of each configuration be the best one for that specific input, and we take the one with the highest value here and use that to define the best configuration for our application for that specific input. And after we have generated that training information, we have generated that theta matrix, we go to the final stage in our techniques, that the final code generation. So basically we take all those information that we previously generate and we set that back to the application. So it's another instrumentation stage here on which basically we are going to perform dynamically that multiplication that will lead to the best configuration, and we take that best configuration and restrict that code to be executed only with that configuration of big and little CPUs. So this is basically the general pipeline of our technique. annotated code provided by the user. We add profiling information. We use that profiling information to later train the application. The result of this training stage is this matrix data that we will use later to carry out predictions in the final code that we generate. So let's go to the evaluation of this technique, and we are going to compare our GCC compiler against Chomp and the global task scheduling that was both introduced earlier in this presentation. And we want to answer two research questions in this work. The first one is about speed. So what is the speed up that we can obtain when we generate applications with our GCC compiler? And the second research question is related to energy. So what is the improvement that we can deliver on top of the similar tools? And the experimental setup that we used for carry out the experiments, the hardware was an Android XU4 big little board with 4 big and 4 little cores, and the software stack was basically an OpenGTK11 for running the applications, and the instrumentation was made possible using Suite. For the benchmarks, we have 8 applications from the problem-based benchmark suites, 6 programs from the Renaissance suite, and 4 programs that we deliver with our GCC compiler. So let's take a look at the results. So the first one, for the execution time, we want to see what is the speed up that we can obtain when you compare against the previous work. So we have executed each benchmark with 4 inputs here, 10 executions per input, per benchmark, and per tool. And we only accept as relevant the results which has a p-value lower than 0.05. So this is the general output that we have here. So each column represents a benchmark, and each row represents an input for that benchmark. In black, we have the benchmarks inputs on which our technique, the GCC, could lead to the faster execution time. In gray, we have the behavior, the cases on Chomp generate an application that could outperform both GCC and GTS. And in white, we have the case when GTS was the best one, and the remaining was inconclusive. Basically, the p-value was unacceptable here. So what you observe here, that's 26 cases out of the 72 combinations of benchmarks and inputs. Our GCC compiler generate was better than the other techniques, and in other 42 cases, the GCC was at least as fast as GTS and Chomp. And the remaining, we observe that Chomp in turn accounted for 3 best results and GTS for only 1. And if you would take one of these benchmarks here and take a closer look, you can see how they differ. So we're taking here the philosopher's benchmark, and you can see here that we have the 4 inputs here on the y-axis, on the x-axis, and the y-axis we have the time in seconds. So for each input, we have the entries for the GCC, the Chomp, and the GTS. On the top of each input, we have the configuration that was chosen by the GCC compiler, and on top right, we have the configuration that was chosen for all inputs by Chomp. And what you see here that these small boxes, they show which configuration, which tool led to the best execution time. And we see here that the GCC compiler, it consistently led to the best execution time. For example, on this last input in particular, it was generating code that was at least 38% faster than the one that was generated by Chomp or the one executed by GTS. And what you can also see here is that the configuration chosen by the GCC compiler, it changed according to the input that we provided to that application. So the next experiment that we want to observe here is the one related to the energy consumption. So what is the improvement that we can deliver with the GCC compiler? In this case here we have a similar chart. And what we observe here for this specific case is that GCC achieved the best results in 20 experiments out of the 72. Chomp was the best one in 6. GTS was the best approach for 2. And here in this case, most of them, they were inconclusive. So leading to the final notes here, we have introduced in this work the GCC compiler, which is high competitive against the other tools present in the literature. It's based on the observation that the function inputs, they often provide enough information to predict the best hardware configuration. Our technique uses a predictor which relies on statistical regression. And for those interested, we have an extended technical report on this topic. Again, thank you.